So let's recap what we've done with matrices so far, okay? Where did we start with matrices? What's the first thing that we did? Right back 2 weeks ago, I think it was. Sorry? The tables, exactly. So we looked at matrix multiplication, okay? And I put a big emphasis on this. In fact, I gave it to you with actual examples. In fact, I've got the sheet here somewhere. Sorry? That was before that. I think it was actually a Friday that we did this. In fact, I've got the sheet here, this one here. Okay, I gave you this sheet here with like loads of tables on here. And I said all a matrix is it's just a table of numbers. Now, clearly, we've moved on quite a long way since these tables, but just remember that each one of these tables, if I strip away everything around it and I'm just left with these numbers, that's a matrix. Okay, so a matrix is just a table of numbers. But you're happy that we're able to now work with matrices without a context around them. In other words, just these numbers. Okay, and yeah, I showed you this from the perspective of multiplication, because I think that's the hardest thing with matrices. Like multiplication is the hardest thing with matrices. If you can get that mastered, everything else is pretty much straightforward, okay? But actually, this is probably the most useful thing in the real world. Like matrix multiplication is where it's used most often, all right? Then what else did we do? Go on, say it. Addition, good. In fact, we learnt two, didn't we? We learnt to add and we learnt to subtract. Okay. Yeah, perfect. And that's what I said. You know, that's the hardest one. That one's the easiest one. What's the condition for this? In fact, just remind me. If I want to multiply two matrices together, what's the condition for those matrices? How can I tell whether the matrix multiplication is valid?
The same, inside it in the second, in first one the second, and
yep.
The first one in the second need to be same, like AMC.
Perfect. So if these are the dimensions of my two matrices, in other words, this is my first matrix, which has n rows and m columns, and this is my second matrix, which has m rows and p columns, then in order to make sure I can do this matrix multiplication, I need to make sure that those inner two dimensions are the same. In other words, the number of columns in the first matrix has to be the same as the number of rows in my second matrix. Yeah? And then to work out the dimensions of the new matrix, how do I do that from this?
You just like taking the A and P.
Yep.
And creating the table.
Exactly. So the new matrix is going to be n times p. Okay. Does that make sense? You remember all that? Good. Fantastic. Addition and subtraction, what do we need? What condition do we need about the dimensions of the two matrices or three matrices that we're adding or subtracting together?
Just it needs to be the same everything.
Yeah. So the dimensions need to be the same. All right? So the dimensions need to be the same if we're going to add and subtract them. Okay? We also looked at scalar multiplication as well, didn't we? So scalar multiplication sounds scary, but really all we're doing is just multiplying a matrix by a single number. So for example, if I said 2 times this matrix, we would get 16, 14, 2 and 0. It's easy, right? So 1, 2 are easy. This one's still tricky, okay? But I think we're okay with it now. We've done enough practice on it, okay? Then we kind of moved on. We kind of took a sidestep and we started looking at all of this stuff, which is like your transformation matrices, yeah? And we looked at this idea of a determinant to work out how many times bigger my new shape is compared to my old one, okay? But what's missing from this list, do you think? So we've done multiplication, we've done addition and subtraction, we've done another type of multiplication. What's missing from this list?
Transform.
We've done that. It's division, right? Just look at the list as it is. Okay, if you think about it, we've done addition, we've done subtraction, we've done two types of multiplication, but we haven't yet done division. We haven't yet done division, right? That's what's left. That's what's left to do, okay? And then we're done, right? Now here's my problem. I cannot divide two matrices together, okay? So if I give you two matrices, A and B, okay? And if I try and divide them by each other, that doesn't make sense in the world of matrices, okay? It doesn't make sense in terms of these operations, okay, so if I actually give you tables which have real life context around them, division doesn't make sense, sorry, it just doesn't, okay? But it also doesn't make sense in terms of the operations. So what I have to do is be a little bit more sneaky about this. So here's what I want you to do. I want you to think about this. If I give you 5 and I try and divide, in fact, no, let me change that to 6. If I try and take 6 and I try and divide by 2, okay? Now let's imagine that we lived in a world where division wasn't allowed, okay? So in other words, I could only use multiplication, addition, and subtraction. I could still work with this. How? Really? Okay, good. So you're realizing that division and multiplication are really the same thing, kind of in disguise, okay? So you're like, if I want to write this in terms of a multiplication, how could I do that? So I take 6, and I want to change this thing to a multiplication. How could I do that? 0.5 or a half. Yeah, good. Okay? Because you realize there's a relationship between that and that. Okay, so 6 divided by 2 is the same as asking the question, what is half of 6? Okay, so 6 times a half. Now here's my question. What is the relationship between 2 and 1/2? Like clearly they must be related because division and multiplication are the same thing. They must be related in some way. So what's the relationship between 2 and 1/2? It's flipped upside down, isn't it? Do you remember the special name for that? Begins with an R, E, C. Good, well done, I heard it. Reciprocal, okay? So reciprocal or refliprical, right? It just means it's been flipped upside down, yeah? Because of course, if you think about 2 as just 2 over 1, then that makes total sense, yeah? So are you happy that you can turn a division into a multiplication by thinking about the reciprocal? Now another word for this, if I turn something upside down, okay, I have inverted it. Does that make sense? Like if you think about a jumper and I turn it inside out, still the same jumper, but it's looked at from a different perspective, okay? So I have inverted it. Same thing here, another word for the reciprocal is the inverse, okay? And that is our gateway to looking at matrix division, okay? So I can't do matrix division as such, but I can find this thing called the inverse, okay? Now let's just stick with real numbers for the time being, okay? Let's suppose I take 3. Now what is the inverse of 3? 1 over 3, okay, 1/3, okay? Now what happens if I multiply these two things together? So I take 3 and I multiply 1/3. It's just equal to 1, okay? So what I should be able to do is utilize this fact with matrices. So let's suppose I have a matrix. I'm just going to call it A, okay? Whatever this matrix might be, it could be something like that, could be something like that, could be that, could be that. It could be any matrix I like, okay? Well, not quite, but I'll come on to that in just a second. So A, okay, what I need to do is multiply by the inverse of A. Now, are you happy? Another way of writing 1 by 3 is 3 to the negative 1. Are you happy with that? Like think about your laws of indices. If I raise something to the power of -1, just means 1 over 3 to that positive power. Okay? So, what I'm going to do is the same thing here. I'm going to take A and I'm going to multiply by its inverse. So A inverse. It's exactly the same idea as this. All right? Now, I want that to be equal to 1. But what's the equivalent of 1 in the world of matrices? Can anybody remember? In fact, I've drawn it on the board. What's the equivalent of 1 in matrix land? It's the identity matrix. In other words, it's just equal to I, the identity matrix. Just that one there. 1, 0, 0, 1. Okay? So you're happy that this property must hold if I'm going to think about division and inverses. Okay? So if I'm able to find a matrix, which is A inverse, then when I multiply it by A, it should just give me the identity matrix. Okay. Now, I'm not actually going to give you a proof because it's a Monday evening and you probably all want to go home. So what I'm going to do instead is I'm just going to give you the formula. So if this is A, okay, so my identity matrix, sorry, my A is just my matrix, and it's just going to have 4 elements, A, B, C, D, okay? Then the inverse matrix, and you can sit down and prove this if you wish, okay, is just going to be 1 divided by the determinant of A, okay, multiplied by, I switch these 2 elements around, so I switch the elements on the leading diagonal around. So a D goes there, and A goes there, and then the rest are just negative. So that's negative B, and that's negative C, okay? Good news is you don't have to remember that formula, it's given to you on the formula sheet.
But if it will be negative, it will start
Yep, absolutely. So we'll look at examples on this on Wednesday, but I just wanted to introduce the idea to you. It's the idea that if you take a number and you multiply by its inverse, it should just be equal to 1. So the same property with matrix division should hold. Okay, if I take A, multiply by its inverse, it should be equal to the identity matrix. All right, and the inverse matrix is given by this. Okay, but we'll do some more work with this on Wednesday, like I say.